A, B of D. And here, instead of I, you even use D as the subscript to suggest that an operator in the Dirac representation is defined as this. For here, I have made a mistake. This will be F0. This will be F0. F0 is independent of time. F0 does not depend on time. Okay? So, and this is the vector defined in the interaction representation of the representation. And now you can see iota S cross del over del T of alpha B0 equal to T and T. Please give me some time. I'll come to your question. This and I, this is X prime T alpha B0, and if you like you can put it B0 equal to 0. If you like you can this is my Schrodinger equation, and dy dt of AI D is equal to minus iota by H cross commutation relation of AI of T and H0 plus this is my equation of motion. So let me recap everything. If I have a Hamiltonian, you see, actually I don't have a choice. If my Hamiltonian is like this, that there is some part which is independent of time. There is some part which depends on time. So this is the interaction done in the theory. All the, you see, we are a physically interacting system. If you were not present here, I would not be able to give a lecture. Okay? I cannot give a lecture in the vacuum. I need some audience. Okay? If I were not here, you would not be listening or learning and quantum mechanics here. As soon as I leave, even before I leave, you immediately start gossiping, start talking to each other. You know this. As soon as I disappear, and then this becomes a chaos. You know this? Randomness appears. So, we are the interacting system. Okay? Right now, we are an interacting. Okay? Good. So, here, the interaction, the operator in the interaction representation is defined by this. Here you see this is F0. You must notice this. Okay? And the state vector is defined like this. Okay? Alright? Now, I say that the Schrodinger equation obeyed by the state vector in the interaction representation is given by this. So what is happening here? H prime of T is involving the state. H prime, which is a function of T, which is the real interacting term in the theory. You see, as soon as you switch off the interaction term in the theory, we become free particles. I go away and you are all free. You can start eating lunch or talk to each other or explain or notes or whatever. Okay? Alright? So, if you switch off this term, there will be this interaction term will not be there, and if the interaction term is there, the state vector would be evolved by the interaction term or by the time dependent part of the Hamiltonian. Okay? Whereas now this is the Heisenberg equation of motion. Okay? So Heisenberg equation of motion with the time development of the operator. Obviously it has to be in the Heisenberg representation. So fine. So here this part is L0 and this is in I of C. Okay? If there is an explicit dependence on time, if there is no explicit dependence on time, then this term is 0. Alright? And now let me leave these two calculations to you. It would depend on you if you would try to do that at home or not. I can only suggest that if you have to calculate this, okay, and so in the interaction representation AI V of I, you will find it here as IC of I. The only thing you need to do is replace everywhere H by H0. H by H0 everywhere, and you will have the same calculation again. You can just read it. Just replace H by H0 and the whole calculation remains the same. Okay? Nothing changes here. Alright? You can just read it. So you have this. You have this here, H0, just in this replace H by H0. Okay? And everything goes the same way, exactly the same way. Similarly, I have erased the calculation of the expectation value. This will also come out to be, the calculation would go simply the same way and it would be, the result would again be the same. So, the computation relation of the operators, they stay as they are. The expectation values of the operators, they stay as they are. Okay? So, then you, if you like now, I could maybe, let me write one step that the supposing I have this force equal to mass into acceleration, okay, plus F equal to dp by dt. For example, this is your Newton's second law of motion. Okay, what happens with this law? You just take the expectation value on both sides of the equation. Okay, if you do that, then expectation value of this is equal to the expectation value of this, which is equal to the expectation value of this. Okay. Obviously here this is my Heisenberg operator, otherwise it would not evolve with time. If it were a Schrodinger operator, it would remain fixed with time, it would not change, but if it's Heisenberg operator, it would change with time. Okay, so obviously this also is Heisenberg operator. What is this equation called there? This is not only this equation, this is the very famous Ehrenfest theorem. Ehrenfest theorem, this was derived 90 years ago. Ehrenfest theorem, it was derived in 1927, exactly 90 years ago. Okay? He derived this equation using wave mechanics, your wave functions and their complex conjugates and so on. In this abstract formulation of quantum mechanics, it simply follows in one line. Okay? So, whatever classical laws of physics you have, they hold true in quantum mechanics, provided we replace the dynamical variables by the corresponding operators and then by the corresponding expectation values of the operators. Just this. This one. We have to bring Heisenberg operator evolved. You see now I have already proved a Schrodinger operator would not change with time. Here I do not know your name, please. A Schrodinger operator remains fixed in time. Its time derivative would be 0. Expectation values. Now don't pay your attention to something else. Pay attention here. I am talking to you right now. you take expectation values either in the Schrodinger representation or in the Heisenberg representation or in the interaction, only one, don't mix up, and the equation would hold. Alright? Try to do it. Okay? Now, I have another 10 minutes time, so let me take an example. Of either a free particle or a harmonic oscillator and try to see what happens. Okay? So, supposing I have Hamiltonian equal to p square by 2m. Okay? This is a free particle, potential energy is 0. So, Hamiltonian is p square by 2m. If it were the Hamiltonian of, let us say, a harmonic oscillator, I would have one more term here. I would have plus 1 half omega square x square. Okay? Alright? I can have many more terms to this. I can have x into t or x square into t if I like. Okay, so I can construct a class of problems by just changing my Hamiltonian. Okay? And obviously you have to remember that you really do not postulate a Hamiltonian, you postulate a Lagrangian, and from there you derive the Hamiltonian using the Legendary transformation. Okay, and then you promote all your variables to quantum mechanical operators, and that gives you the Hamiltonian operator of a particular theory. But I can define a particular Hamiltonian, let us say this or some other. Okay, now let me for the time being drop this term. Okay, and let me see what happens to this. So, if I want to study the dynamics of this system, it's a free particle. Okay? As soon as I leave from here, you will be a free particle. You can do what you like. Okay? You are not bound by any potential energy. As long as I am there, you are supposed to be a little bit disciplined. Alright? Fine. So, I calculate iota S cross d by dt of x. This is the time development of this operator, which is in the Heisenberg representation. Okay? Alright? And this should be equal to iota S cross for what? No iota S cross. X, because I have this here equal to minus iota by S cross times the times x of h and h of s. Okay, and if there were an explicit dependence on time, which is not there, so this guy is straight away 0, and this is like this. This I have written as equal to iota S cross equal to this. So I put this iota S cross here, this guy goes to 0, and now this you have to calculate. H is here, let us say p square by 2m. Okay? Alright? And you have to know how to calculate the connotation relation of A, B, C or A, B, C. Look into your books, find out the formulae. This should be your A, B, C plus B, C, A. Okay? So, using this, you can find out this is P into P. You can solve this, and then use the fundamental relations of HP equal to iota S cross. Okay? So use the fundamental position relations, and you can find out its value. And this should give me by dt equal to d of h by n. Okay? Alright? This would be the time development of the x, operator x. Similarly, you can find out the time development of t. Okay? Now you have two equations of motion. This, I think, if you permit me, let me better erase this. Okay? Then I would be more free to write things. Could I remove this?
Yes.
Okay, now I could use even this part of the board and all right. So now dp by dt, similarly you can find out minus I will have draw p of h of h plus the other term, this goes away, and this is p and this is p square by 2n. So this would be just here. Okay? So given any problem, in one problem I am trying to solve a class of problems. Okay? If I am given some Hamiltonian, it can be a function of p, it can be a function of x. So Hamiltonian by definition is a function of the various variables, q's and v's. Okay? And possibly time, if you want to introduce x is time dependent. Okay? Now, what you are supposed to do, I am teaching the method, how to do it. Use the Heisenberg equation of motion, determine the time development d by dt of the coordinate x or q's for all the as many q's as you have in your theory. Okay, you have to determine these equations. Similarly, you have to do the same for, so these are two first order equations of motion. If you like, you can find out second order equation. If you like, you can solve it further. Let me just try to complete this. So you will need formulas of this type. Okay, you will need formulas of this type, and you can eventually solve this. So here, now dx by dt, for example, is dh by m. This would give me x of h equals to this, let me call it a function of time t. This is equal to this by this into t. So dh by m into t plus a constant c. Okay, very just first year calculation. Okay, you put dt here and integrate. So this is what you get. And now this is the constant of integration. You put the initial conditions. So your initial conditions are defined by, let us say, x of t, x of 0 is x of x is equal to 0. So what is this? This is, what is x of 0? This is x of s, which if you like also put it like this, or you have to understand it conceptually what it means. So this gives me the initial value. Okay? I know the value of, so this constant would be just x at 0. Okay? You put t equal to 0 here, this is x of 0 here, and then this is dx by m, and what do I get from this equation? I get this is equal to 0, which means d of h, which is the function of time t, is equal to the constant. d by dt of this guy is 0, which means this is equal to constant, and this would essentially be the same as d of h time equal to 0. If you like, you can call it of 0. If you like, you can call it d of s. So this is the same guy all the time. Schrodinger operator is the same thing, which is Heisenberg operator at time t equal to 0. any Heisenberg operator at time t equal to 0 is identically the same as the same operator in the Schrodinger representation. Because there it does not evolve with time. So that gives me the initial condition. Alright, I can put these things back here, and what else do I need? So now I want to demonstrate one particular point. Let me calculate its commutation relation of xh of t and x of xh of 0. What should this be? This is equal to commutation relation of t of x of 0 by m into t and x and 0. And this, no, not this, this plus this, comma, x of f0. This commutation relation, and this is nothing but t by m, t0, f0 plus. So this would be equal to iota x cross plus there would be one more term which is x of 0 with x of 0. This would be 0. So what you get, this is equal to iota x cross times d by n. So it's not that, it's a simple bracket, okay? It's a simple bracket. So, you see, now by taking some very simple example, you are in a position to be able to see that these two guys are different. This is the Heisenberg operator at time t equal to 0, which is the same thing as the operator in the Schrodinger. Okay? And this is your Heisenberg operator. The commutation relation of this you can find out as this. Now, how do I create a class of problems? From here, I create 4 terms. If I take here, for example, plus 1/2 m omega square x square, okay, or this is the same term as plus 1/2 dx square. This is one-dimensional harmonic oscillator. It be px. So you do the same calculation again, results would be different because there is one more term here sitting there, 1/2 dx square. So in all these commutation relations there would be extra terms hanging everywhere, and you will have again two equations of motion, first order equations of motion, dy dt of x, dy dt of t. If you like, you can solve one with the help of other, and you will end up with the same x double dot plus omega square x equal to 0. The equation of motion, or it gives you sine and cosine functions. Okay? And so everything you can do, I leave it to you as a home exercise, and I suppose I am more or less through with the concept of the Schrodinger, Heisenberg and Dirac representation of the interacting theory. I would still be here just one and what else, and you can do lots of problems based on this from next week, from Monday, or not from next week. In the next week, I would be doing in detail one-dimensional harmonic oscillator, and I propose to cover it up in 3 lectures, and then I will stop. Okay, so, Rajan, please, go ahead.